Moving on to the second part of our discussion, we're going to talk about the study of the expanding universe and what this tells us about the types of matter and energy that the universe contains. We need a little bit of background first. So we're going to start with an overview of the electromagnetic spectrum, by which we mean light. And the main thing you need to know about light is that it has different wavelengths and energies. The whole electromagnetic spectrum extends to much shorter wavelengths of light than we can see with our eyes and much longer. Visible light is shown in the middle there. Bluer light has shorter wavelengths and redder light has longer. So when we say that light is bluer or redder, we're really referring to its wavelength. Bluer means shorter wavelengths and redder means longer. So here's a little animation just showing you how the color of light relates to its wavelengths. Red light, long wavelengths, blue light, short wavelengths. And there are processes that can change the wavelengths of light. One of them is shown here. This is something called the Doppler effect. You might be familiar with this in the form of sound. If you've ever noticed, for example, the pitch of a siren changing as an ambulance passes you, that is the Doppler effect, changing the frequency of sound, but it can also change the wavelength of light. And that happens if an object is moving toward you or away from you. You can see in this little animation how the wave fronts of the wave that it emits get compressed in the direction that it's moving and stretched apart. And that causes the light to appear to be blue shifted to shorter wavelengths if the object is moving toward you, and shifted to longer wavelengths, red shifted if it's moving away from you. This is related to something that we observe when we look at distant galaxies. What we find is that if we study the light from distant galaxies, we see that it is increasingly redshifted. In other words, the farther away a galaxy is, the longer the wavelengths of its light by the time it reaches us. And we can tell from this that galaxies are moving away from us. And the farther away a galaxy is, the faster it's receding. So this is illustrated just by this little schematic diagram here. The distance of galaxies in the x-axis here, the speed they're moving away from us, going upward. So the farther away a galaxy is, the faster it's moving away. A picture like this is known as a Hubble diagram, after Edwin Hubble, who plotted this relationship in 1929 using distances to galaxies that were measured from those Cepheid variable stars. The reason, of course, that galaxies are all moving away from us is that the universe is expanding. Every point is moving away from every other point. And an analogy that's commonly used for this is the surface of a balloon. If you're on the surface of a balloon and that balloon is being inflated, every point on that surface is moving away from every other point. There's no particular center to that expansion. Everything is just moving away from everything else. And this is also why the wavelengths of light are increasing and galaxies are redshifted. I described the Doppler effect because it behaves similarly to that, but it's not exactly the same thing. What's actually happening is that for the most distant galaxies, their light is getting stretched out by the expansion of the universe on the way from the galaxy to us. This is what we call a cosmological redshift. It's the stretching of the wavelengths of light by the expansion of the universe. The expansion of the universe implies a moment when everything in the universe started from a single point. We call this the Big Bang. And as we'll see, the evolution of the universe after the Big Bang tells us a whole lot of information about the various components that make up the universe. So before we get to this, we need a little bit more background information. These are the basic building blocks of ordinary matter. You and me and trees and planets and stars are all made of protons, neutrons, and electrons. These are the basic components of atoms, which have protons and neutrons bound together in a nucleus with electrons surrounding them. It will also be important for our discussion to know that protons are positively charged and electrons are negatively charged, and that particles with similar charges attract and opposite charges repel. Also, the electromagnetic force that does that is extremely strong. The electric force between two protons is 10 to the 36, by which I mean a 1 followed by 36 zeros, 10 to the 36 times stronger than the gravitational attraction between those two protons. Right now, the ordinary matter that we're interested in is the lightest elements on the periodic table: hydrogen, helium, and lithium. These are the elements that were formed very shortly after the Big Bang. Everything else that you see on this table was formed later by various processes in stars, which is the topic of a whole nother talk, which I hope you get to hear someday. Here are some schematics of hydrogen and helium atoms in particular. A hydrogen atom is just a proton with an electron bound to it. A helium atom consists of two protons and two neutrons in the nucleus, and then two electrons surrounding them. Although we can also have a different variety of helium if we just get rid of one of those neutrons. So returning now to the Big Bang. The universe started in a point of incredibly high temperature and density, and then it rapidly cooled and expanded. And during the first several minutes of the universe, the temperature and the density were high enough for protons and neutrons to fuse together into the light elements that you see here: deuterium, which is hydrogen with an extra neutron, those two different types of helium, and lithium. The nuclear fusion reactions that enable this are extremely sensitive to both the temperature and the density. And what that means is that by comparing our models of this process with the observed abundances of these elements, we can learn how much ordinary matter there actually is in the universe. This is the result of that comparison. So here is a plot. These colored lines are our predictions for the abundances of these different elements for different amounts of normal matter in the universe. These boxes here, these yellow boxes, are what we observe when we try to measure these abundances. Some of these boxes are large because some of these are difficult measurements, but what you can see is that there is a region where they all line up, and that gives us constraints on the amount of normal matter in the universe. And what this tells us is that less than 20% of the matter in the universe can be made of protons and neutrons. Remember that we can measure the total amount of matter in the universe by counting up the most massive galaxy clusters. And this total amount of matter is much higher than that amount of ordinary matter that must be present after the Big Bang to give us the right amount of helium and the other light elements. So the conclusion then has to be that less than 20% of the matter in the universe can be made of protons and neutrons. If it were higher than that, then the abundances of these light elements would not match what we observe. We're going to move forward in time now to when the universe was about 370,000 years old, and our next important cosmological event occurred. We need one more piece of background information for this discussion, and it's shown by this little animation here. The red circle that you see represents a proton, and that little gray one is an electron. Notice that they are not bound together in an atom. They're just floating around freely. And that little squiggly line that you see there is a photon. It's a particle of light. If light encounters a free electron, it will scatter. It will essentially bounce off that electron and go off in a different direction. This is important because of the conditions during the first 370,000 or so years of the universe. It was so hot that protons and electrons could not combine together into neutral atoms, and therefore the light was continually scattering off of those free electrons, which made the universe opaque. However, at an age of about 370,000 years, the temperature became cool enough for neutral hydrogen atoms to form, and then the universe became transparent. The light no longer had free electrons to scatter off of, and so it was able to stream freely through the universe. This is the light that we see today as the cosmic microwave background radiation. It fills the universe, and it has been cooling for about 13.7 billion more years to now reach a temperature of 2.725 degrees above absolute zero. It is almost exactly 2.725 degrees everywhere. But if we look at this radiation on a much finer temperature scale, then what we see is that, in fact, there are small variations in temperature across the sky. This light is giving us a snapshot of what the universe looked like when it was 370,000 years old. And these variations in temperature are telling us about variations in density. And because these variations are so small, we know that the matter in the universe at that time must also have been distributed very smoothly. However, the universe is not smooth today. We look all around us, we see galaxies, we see clusters of galaxies. The universe is clumpy. So how did we get from the very smooth distribution of matter that we see at an age of 370,000 years to the clumpy distribution that we see today? The answer to this, as shown in this simulation, is gravity. Regions that are slightly more dense than their surroundings have a stronger gravitational pull, and that enables them to pull in more matter from around them. That additional matter increases their gravitational pull a little bit more, which enables them to attract even more matter, and so forth. The dense regions become denser and denser, and eventually grow into large structures over time. So the simulation that we've just watched, this is a movie from a large simulation of the distribution of dark matter in the universe over time. It's centered on a massive cluster of galaxies, and you can see how it starts with a very smooth distribution that develops into a much clumpier structure over time. This is an image from another cosmological simulation of the growth of galaxies and the structures around them. I've just included this because I really like this picture. This is from a project called the Illustris project, which simulates both dark matter and gas and stars. So what you're looking at here is, again, a region that's like a massive galaxy cluster. All the blue filamentary structure that you see is the distribution of dark matter, and then the brighter colors are showing you gas. So this is our picture for the growth of structure in the universe. This is how we got from that smooth distribution at 370,000 years to what we see today. However, there is a problem with this. If we look at the size of those temperature variations in the cosmic microwave background radiation, and then look at the sizes of the galaxies and the galaxy clusters around us today, and then calculate how much time it would take to get from one to the other, we find that not nearly enough time has passed. The universe today is much clumpier than we can explain by looking at those temperature fluctuations. In order to understand the solution to this problem, we need to go back to this process of recombination and the conditions in the universe at the time. Recall that right before this process of recombination, the universe was filled with free protons and free electrons and light that scattered off of those free electrons. And then when the universe became cool enough for the protons and electrons to combine, the light stopped scattering and streamed freely. Also recall that protons are positively charged and electrons are negatively charged. Although the protons and the electrons are not bound together into atoms at this point, they still interact via the electromagnetic force, which you'll recall is much stronger than the force of gravity. So the universe is filled with light that is continually bouncing off the electrons and exerting pressure on them, and therefore also exerting pressure on the protons that are interacting with those electrons via electric forces. What all of this means is that the overdense regions of matter cannot begin to collapse due to gravity while they're in this state. The electrons that are coupled to the photons via the photons bouncing off of them all of the time prevents this collapse. The protons can't collapse because they're bound to the electrons by the electric forces, and the photons are bouncing all around, keeping the electrons from collapsing as well. It's only once the protons and electrons are bound together into neutral atoms, then the light stops scattering and stops opposing the collapse. And after this, ordinary matter can start to grow into larger clumps under the influence of gravity. However, we have already learned by studying galaxies and galaxy clusters and the abundance of the light elements that most of the matter in the universe is not ordinary matter at all. It's dark matter, and dark matter doesn't care at all about what the light is doing. What that means is that denser regions of dark matter can start to collapse under the influence of gravity at earlier times, before this process of recombination, when the protons and electrons became bound together into atoms, before that process took place. And this is the solution to the problem of how the structures in the universe got to be the size they are today. Dark matter gives us a head start on the process of the formation of these structures and allows more time for them to grow. If most of the matter in the universe were ordinary matter made of protons and neutrons, then galaxies and galaxy clusters would not be the sizes that they are today. So we've seen many pieces of evidence that most of the matter in the universe is dark matter. What is dark matter? We don't know. This is one of the major problems facing astrophysics today. There are a lot of theories. Most of them suggest that it's some type of subatomic particle. And there are a lot of experiments in particle physics that are currently working on this, but this is not yet a solved problem. So stay tuned, keep paying attention. Hopefully we'll figure this out sometime soon.